like I said, our focus today is on recursive rules. Now, when we define a sequence recursively, what that means is, how do I use my previous term to get the next term in the sequence? Give me kind of like, it's almost like an algebraic representation of that, or a sequence representation using my t's in an algebraic format. And so we're going to develop the sequence 1, 5, 9, 13, etc. as a recursive rule. And the way we do that is to consider some patterning first, so you can see what's going on. So the second term is equal to the first term plus 4. We all decided that that was okay. To get the next term, we just add 4. So term number 3 is equal to term number 2 plus 4. And what would the next one be? Term 4 would be term 3 plus 4. So what I'm trying to get at here is that this, we're adding 4 to the previous term to get the next term. So that next term is one position more than the previous term. So term 2 is one position more than term 1, term 3 is one position more than term 2, and so forth. And hence, when we define this recursively, what happened there? That should be term n plus 1. Just doesn't like me, won't let me go to my eraser. Sorry, Tn plus 1, let's write it in there, is the previous term Tn, so one position less, and then plus 4. So that is the crux of a recursive definition. So it's kind of an algebraic approach, but we're using the previous term to get the next term. So that connection between Tn plus 1 and Tn is important. Tn plus 1, one position more. It's a subscript. It's a positioning. N represents a positioning. N plus 1 is one position more. And then we're adding 4 to whatever that term number is. Now, like I said at the start, I could have lots of different sequences where the pattern is plus 4. So I need to determine a start point. Usually it's term 1. If you don't write a start point, you will lose a mark. There's always a mark for this start point. So the first term for this sequence is 1. So we must define the start point. So then we know the sequence goes 1 plus 4 makes 5 is the next one, plus 4 makes 9, and so on, as opposed to starting at another number. So that is a recursive definition. That's it. So let's try the next one, see if you can do, well, this one. Actually, I think I've already given this one to you. So with this next sequence, you've got 5, 7, 9, 11, 13. So to get to the next term, we're adding 2 to the previous term, starting with 5. First term is 5. So next term, previous term plus 2, and this is how we would write that. So again, it's that same idea. Your recursive definition, Tn plus 1 means the next term. How do I use the previous term to get to the next term? And I do that by adding 2. Now, we do need to define the first term, however, in our sequence. And so, really, we should say T1 equals 5 here as well. So I'm starting at 5, and to get the next term in the sequence, I'm adding 2 each time. Yep.
In like a test question, would you get asked, like, give the...
Yeah.
Would that be worth like 2 marks?
Yes. So you definitely need this, and that's always worth a mark, that first term.
2 marks.
And so it would be, 2 marks for a recursive definition. That wouldn't be that straightforward though, just saying. We're starting nice and easy, but yes. 2 marks, maybe more depending on the type of recursive rule that we're using. And then this is applied into applied questions and finance questions and things like that. So this is the real bare basics at the moment. All right, so recursive rule, because the reason why it's called recursive is we're using terms to get another term. So there's 2 types of rules. There's a general rule and there's a recursive rule. So work that we've done on linear functions actually represents a general rule for this type of sequence, where you don't need the term before to get where you want to go. Whereas here, we do. We need the term before to get the next term each time. So we're always relying on the previous term. So if I wanted to know what term 100 was, I actually need term 99 to do that. With our linear rules that we've done in the past, we could actually just sub in 100 into the rule. So that's the difference. We're using previous terms to get the next term. So the idea highlighted in yellow is that we need two parts. We need the rule, and that links to a previous term, and we need a start point. Usually it's the first term. In a contextual question, sometimes that's referred to as T0, an initial value. T0 is initial. Or you could be given, there's no reason why we can't be giving you term 3 or term 5. And then you could back project to term 1 if you want. As long as you've got a term, it doesn't matter. It fits, it sets the sequence in place regardless. Now, if you have a scenario where you are only using one previous term, so we've done a couple of really simple ones where we're just adding, then we call that a first order recurrence relation. And that is the types of sequences we're going to be dealing with formally in the Year 12 course. So when you're only using one. However, we will extend you a little bit because we know Fibonacci uses two previous terms. We did that yesterday or when I saw you last. But the ones that use just one previous term, where you can have a multiplied value or adding or adding a constant, that is your first order recurrence relation. That's just a formal word that is in your dot points. So you do need to be familiar with it. All right, so let's just get some practice, see if we can generate some sequences and go from there. So you've got, that first statement is from the previous question. You've got an example here where you've got two different sequences. I want you to tell me what that sequence is in words, and I want you to generate the first four values of that sequence using the rules. When defining a sequence, talk about how we're going to get the next term. So to get the next term, we add 8 to the previous term, starting with 10. Don't forget to add your start point. Whereas in B, what are we doing to get the next term? To get the next term, we multiply the previous term by 3 and then subtract 1. And we start with -5. So term 1 is -5, term 2. So this one's a bit trickier than the previous because there's two parts to the rule. We're multiplying by 3 and then we're subtracting 1. Joe. Oh, sorry. Multiplying by -5 first and then subtracting 1. Sorry, -5 multiplied by 3. Then subtract 1 takes us to -16. And then term 3, follow that same pattern. 3 times -16, that previous term, subtract 1, -49, and so on. Term 4, 3 times -49, subtract 1, -148, I think. So can you see how you need that previous term to get the next term? If I asked you for term 10, you'd have to go through the motions. Find term 5, term 6, term 7, term 8, term 9, term 10. So at this point in time. I will show you how to do this all on the calculator as well, and the calculator will generate all the list of all the numbers. So it's pretty cool. At some point. All right, next one. So make sure we're subtracting 6 from the previous term. So there's your Tn plus 1, the next term, Tn, and then we're subtracting 6. With T1 is 20. So we start at 20 and then we take 6 each time as we go along in the sequence. All right, next one. So next one, similar. This time you've got the recursive definition. So to get the next term, we multiply the previous term. Then add 7. Starting with 4. So we start with 4 times by 2, add 7 to get the next term. So you might like to write that out. I always find if it's not a direct adding or subtraction, it is helpful just to write out your working there. So 2 times the previous term, which is 4. 2 times 4 is 8. 8 plus 7 is 15. You've got 2 times 15 plus 7. 2 times 37 plus 7. I think that's 81. And term 5, 2 times 81. And so on. What do we say? First 5 terms. So again, just practicing. Going from the words to the recursive, generating the sequence of numbers. All right, so here I said we've got to define a term. Usually it's the first term, but this one's the 5th term, the 3rd term I mean. So we know term 3 is 5. That's okay, we can still generate this sequence. Think about how. So remember, Tn plus 1 is the next term. So to get term 2, we've got term 3 is 2 times term 2 plus 7. So we know term 3 is 5. It's like solving an equation here. We've got to undo the plus 7, subtract 7, and then we divide by 2. So term 2 is -1, and you can always check that by going forwards again. 2 times -1 is -2, plus 7 takes me to 5, and term 3 is 5. Once we've got term 2, then we can do the same thing and find term 1. So term 2 is 2 times term 1 plus 7. So -1 is 2 times term 1. So term 1 is -4. So it has got a star next to it, the next one. But this one, so term Tn on 2 or half Tn is my preference. And halve the previous term and add 2 to get the next term. So again, we just keep going through the motions. We need the previous term to get the next term. That's the whole point of recursive rules. Now, let's look at B. B is a little bit more challenging. And the reason why it's more challenging is you've got this n plus 2 and this n plus 1 and this n, and we're only used to n plus 1 and n. But actually, don't be scared by it. Tn plus 2 just means what? Yeah, it's 2 positions away. 1 away from n plus 1, but 2 positions away from Tn. So the reason why we would use Tn plus 2 is because we are defining a sequence that requires 2 terms. All the sequences we've done so far, which are the first order linear recurrence relations, are using just 1 previous term to get the next term. This sequence, we need the 2 previous terms. So in actual fact, this sequence is defined as to get the next term or the term after the next. We start with the original term and add that to the one after that to get the next one after that. A little bit confusing, but let's put the numbers in. Term 3 is going to be term 2 plus term 1. That's it. In order for us to find term 3, though, we need both of those 2 numbers, which we have. We've got them. Term 1 equals term 2. They're both equal to 1. So term 3 is 2, yeah. And then term 4 will be the previous two terms. Term 3 plus term 2. Term 3 is 2, term 2 is 1. So term 4 is 3. Term 5 is term 4 plus term 3. So term 4 is 3. Term 3 is 2. So this is our sequence. I'm going to write it like this just so that you can see it, because it's one you may or may not be familiar with. The next one would be 8 and so forth. We came across it the other day for those of you that were here. What's the sequence? 1, 1, 2, 3, 5, 8. What sequence is it?
2 previous.
Yeah, you add the 2 previous to get the next one, but it's got a special name, this particular sequence, these numbers in particular. 1, 1, 2, 3, 5, 8. The Fibonacci sequence. Yes, it's the Fibonacci sequence. So we came across this the other day. All right, you need to define the first 2 terms. Who was listening? Why do we need to define the first 2 terms? Not just the first term. You're using 2 terms to get the next term. So we must define 2 terms. Similarly, if we had a sequence where you use 3 terms, then we'd start at Tn plus 3. Okay, so this one is what we call a second order, not part of the formal course, but I just thought Fibonacci, is pretty interesting sequence and comes up in lots of things in real life. But you will only be assessed on first order. So the reason why this one is because we're using 2 previous terms to get the next term. And anyway, I hope you like my little cartoon there. So we've spent a little bit of time generated sequences from a rule. Now, let's see if we can write the recursive rules from the sequence. Go back the other way. Okay, so for us, remember, it's only a first order linear recurrence relation. So the best it can do is times something plus or take something. When I say times something, that could be a fraction. Like this last one. So -2, 700, so -900. Each of these numbers are reducing by a third. Or they're times by a third. Or divide by 3. You could write that as Tn on 3. That's not wrong. It just doesn't look right to me, but it's certainly not wrong to do that. That is perfectly fine. Don't forget in each of these, like I said, define that first term. And what about this one, F? They're not very exciting. So you had a double plus 1 previously, and what's this one? Double minus 1. So 2 times the previous term, subtract 1. The reason why they're not very exciting is because they're not that straightforward to determine off the top of your head. And that's what the next question is about, which we're not going to do right now. This one here, those numbers aren't nice, and that's going to be hard to come up with that kind of rule. So we'll start with that tomorrow. What I want you to do now, I'm not going to give you homework on this stuff, obviously. I want you to go back now. We've got a few minutes and finish off these couple of area questions that we didn't get to earlier on.